Okay, this is lecture 41. In the last class, we were discussing about the continuous time linear equalizer, and we were discussing the design steps for that. So let me just write it down, continuous time linear equalizer, and also called as CTLE. And the architecture which we have seen is this. So let me just do RS, CS, and current source by 2. This highlight Vn by 2 and minus Vn by 2. And we had a load capacitance which was coming from the following blocks, which you cannot do anything with. You can just accommodate in the system, TL, and let's say call this as VOP and VON. Okay, so this is generally the boundary of your CTL. Boundary of the CTL means CL is coming from the following blocks. That's not in your hand, more or less. Now, if you look at the design for the CTLE, the things which you know beforehand, CL is fixed in the sense what is coming from the following block. Okay, then channel loss will actually decide what kind of gain do you need. Channel loss will decide what is your A peak by A DC ratio. This will have a channel loss. The other thing is the common mode output voltage, VCM out. This is quite important in this circuit because it will decide the other poles in the system. So common mode output voltage, this will be decided by the following blocks, more or less, unless you use some level shifters in between actually. Following blocks like samplers or other variable gain amplifiers, VGA, etc. Okay, so this is the thing which you know about this equalizer. The other design parameter which you know, that GM over ID for input pair. It's like you increase the current, you can increase the GM value as what you need. Okay, so all these things are something which you know even before finding what is the poles and zero location. Now the transfer function for the CTLE is your ADC 1 plus S by omega Z, and yesterday we saw that the one pole is just a scaled pole of your zero location, and the other pole is the pole due to the output capacitance and the low resistance. So I will just write ADC is GMRL by 1 plus GMRS by 2, omega Z is 1 by RS CS, gamma is 1 plus GMRS by 2, and omega P2 is 1 by RLCL. Okay, we need to find the values of RL and what kind of GM value do we need. So the transfer function which we have seen for the CTLE is you can have some DC gain and then peaking at the Nyquist frequency. So and then coming down due to the second pole in the system. So this is Fs by 2, where Fs is a data rate. This is mod of Hs. Okay, you have this ADC and A peak, right? So what do we know about the system? We know A peak by ADC. That means I have Hs evaluated at omega equals to omega peak, which is 2 pi Fs by 2 is equals to ADC 1 plus J omega peak by omega Z 1 plus J omega peak by gamma omega Z, and I'm just writing so that there is no discrepancy in this part, omega P2 and mod of this. This is something, means you know left hand side, you need to find the variables on the right hand side. That's the whole part. And if you see the thing is you need to start with something as, what happened? Yeah. So either you define A peak by ADC or you define ADC and A peak independently. That's a variable parameter in your hand. Okay, but this expression is in terms of omega Z by omega peak. Sorry. Yeah, you can say either omega Z by omega peak or omega peak by omega Z and omega P2 by omega Z. Sorry, omega peak. Right? This is this expression. The other thing, the last comment which I made in the last class was that the derivative of this transfer function at the peak point goes to 0. So I will use another equation where I say d by d omega of mod of Hs evaluated at omega equals to omega peak is equals to 0. This is the second equation. Okay. So now you start the design. You know GM by ID for the input pair transistor which you are going to use is fixed to begin with, GM over ID. So you start with some GM parameter. Okay, if you start with any GM parameter, that will give you ID. You start this much GM over ID ratio is fixed, that gives you ID. As soon as you have ID and you know VCM out, so you get RL. Supply is fixed. Once you know RL, your omega P2 is, you got it, because CL is coming from the outside parameter. Okay, the only other part in the omega P2 is CL, right? RL, you know the CL consists of two parts. One is CL from the, let's call me a CL0, which is coming from the load side. Other is CL coming from the input pair itself. Okay, so if you have a transistor model that as you increase the GM, you are going to increase the CL also, you can accommodate that. So this is from, let's say, following load. And the other one is CL1 from input pair itself. So you know omega P2. Okay. Now if you look at equation 1 and 2, I want both of them to be satisfied. So I know omega P2 by omega peak. Then if I know ADC, so it's like this. In ADC, by knowing GM and RL, you know the GM RL part, and the bottom part is 1 plus GM RS by 2. If you know GM RL, you know you want certain ADC gain. You can find RS in that term. So only thing we want to know is what is omega Z by omega peak. And that should be the common solution from equation 1 and equation 2. Okay. You find that, so you get a certain GM value, you find omega Z by omega P in this particular manner, and you do this like maybe a scripted simulation, that you do this process and find the minimum value of GM for which you can satisfy all of these, because that will be the most power efficient design, which gives you all the parameters required. So you start with a GM, it's like varying GM, and find a minimum GM. Find minimum GM for which 1 and 2 are satisfied. Equation 1 and equation 2. So this is like, because the equation turns out to be more of a non-linear equation, so it's like you have a quadratic, not non-linear, but you have more parameters. So you need to solve it more empirically rather than finding a single form solution. Like a closed loop form. You do not get a closed loop form that easily. But with all these things, you can get the exact RS. So once you get your omega Z, you know your RS, you can get the CS value, right? So this will give you the CS value. So you got all the parameters now. And the thing which needs to be noted is that actually whatever RS value you have got here, right? For a small signal picture, you have the impedance coming from here and impedance of the current source also. So whatever RS value you calculate in a scripted form or a MATLAB simulation or something, you need to take the GDS into account when you later put the RS value in a real circuit. And similar things will happen for the capacitance. The extra parasitic capacitance will exist here due to both the top and the bottom transistor. So you need to accommodate that within the CS value. Okay. So do you have any questions still now? You need to find a omega Z by omega peak, which is yeah. If they do not give a different solution, that means you cannot satisfy both of them. You need to change your GM value. You will get a range of GM values, but then you pick a minimum GM value, because minimum GM value will correspond to your minimum current. So that's the power part. But once you get all these values, right, you see that if I get all the values from here, it's a plug-in issue in case of schematic. Otherwise, you have to vary which one is, when I change my 0, how does my pole change, so that I get a peak value. Okay. So now can you comment that what is the maximum peaking frequency? So let me say VCM common mode output potential is something you want for the following blocks. CL is something which is forced on you from the following blocks, and you want a minimum current. Sorry. So you want minimum current solution, minimum I. What do you see? What's the bottleneck in all this? And the thing is, okay, minimum I, that is all these parameters together, they are actually limiting, let me just tell you, they are limiting your omega peak. Can you get that from this? So you have a VCM out, and if you want a omega, so you see, if you have a VCM out, that means you need to, if I want the peaking frequency to be moved further away, I need to reduce the RL, the load resistance. If I reduce the load resistance, that means I have to burn more current because I want the same BMR. And use of active transistors here will be limited because of the headroom on the supply side and the capacitance which is going to it. Right? So this particular implementation, if you are not doing anything more on this, is actually limits your peaking frequency in the system. And one other way to quantify that is that from CTLE, if you look at the, I don't call it, so one of the metric which you say you want maximum gain. Let me just say this is CTLE figure of merit, which it is not, but I'm just say figure of merit 1. Let's say you want maximum gain, right? You want higher peaking frequency or maximum peaking frequency you can get, and you want wider bandwidth, ideally, right? Large bandwidth. These are the ideal parameters which I want to have from the CTLE. I have not taken the power into account yet, but this is what I want if I have infinite power in my hand. Okay, so you see that maximum gain, so maximum gain is like the DC gain. Let me not say the maximum gain, let's say it's a DC gain. Larger DC gain means large swing, signal swing. So large DC gain. Okay, if you have a large DC gain, means the whole signal swing will be increased. So you have DC gain, you have higher peaking frequency is minimum of omega P1 by omega P2. Large bandwidth is the far off pole. Okay, so if let me say DC gain is GM RL by 1 plus GM RS by 2. Let's say omega P1 is the dominant pole, which is, so higher peaking, no, this one is, let's say omega P1, which is into far off pole is omega P2. Do you see any parameter missing what we want from the CTLE? Anything missing here which you want for ideal CTLE channel loss compensation? So see, I have only got the DC gain, I got the peaking frequency, I got the far off pole. What is missing in this? Peaking gain, right? Okay, so we have, let's say in place of the peaking gain, if you have, in place of the DC gain, you have A peak by A DC, which is the maximum loss compensation you can compensate. Okay, so A peak by A DC is, this is coming to a different figure of MAD actually. So this is minimum of omega P1 by omega P2 by omega Z. Okay, now let me just, you have omega P, let's say omega P1 by omega Z, and you have far off pole is omega P2. Okay, is anything wrong with this equation? Can you get anything missing here? So let me just write it this one as omega peak by omega DC. Let me just say ADC into A peak by ADC into bandwidth. Okay, where you have minimum of omega P1 by omega P2 by omega Z into omega P2. Okay, and this one is ADC gain is GMRL by 1 plus GMRS by 2, this into omega P1 by omega Z into omega P2 thing. This I can say 2RL by RS. Okay, this one is 1 by omega P1. This is actually gamma times omega Z into omega P2. So now you have, so gamma is GMRS by 2 into 1 by RLCL. So let me just say that this is equals to GMRS by 2. So you have this cancels out, you have GM by CL. Okay, so in this case, the metric which we started, right, that was like we are considering the omega peak frequency itself. Okay, but what we actually require is a larger channel loss compensation, that is A peak by A DC, larger swing, that is larger ADC, okay, and a larger bandwidth, which is equal to larger omega. Larger the bandwidth means the far off pole should be much away. So let's not consider this one, consider this part, ADC into ADC, A peak by ADC into bandwidth. And in this case, we are still not considering the power. We will come to the power in the next section. Okay. So you see, you have all of this is basically turning out to be GM by CL. Okay. And GM for a particular technology, whichever you are using, and if CL which you are considering, the CL is coming as a, it's not the extra capacitance which you are putting in the circuit. Is the capacitance which is coming from the following gates of the transistors, whichever the circuit is following. So CL is also coming as a technology parameter. So in the end, this whole metric for the CTLE is getting limited by the technology. If you are having a better technology where you can get a better GM by CGS of the following transistor, you can improve the CTLE performance. Okay. So can you do anything to get rid of the CL? Or if you still want to increase the bandwidth of the system, what should be the first way to do it? Pardon? Tune it with the inductor. So if you, let's tune it with the inductor at which place? So you have this load resistance RL, which is going to be there for a DC gain. Capacitance CL is coming on its own. How will you, where will you put the inductor? Series with R, series with C. Okay, so you can work out both the cases, whether it is series with R or series with C. So let's say you have series with, so now this is the load RL, let's say load inductor LD, and parasitic capacitance or the load capacitance is CL. Okay, so previously in a CTLE transfer function, you have ADC. I am writing it again and again because this will help you to understand what parameters affect the CTLE performance. Okay, and 1 plus S by omega P2. So which is the bandwidth limiting factor because of CL? Omega P21, right? So this is the bandwidth limiting in your regular case. Now in place of only RL and CL, I am having a LD also there. Okay, so what will that do? So let me just write it as a input impedance looking in, or Z in, you have Z in is equals to 1 by SCL in parallel with RD plus, sorry, RL plus SLD, right? So you have RL plus SLD into 1 by SCL and SCL S square LD plus SCL RL, right, plus 1 whole divided by SCL. So if I take all this thing into account, my new HS will be ADC. So you saw that, right? I am not changing anything to the input pair, the high frequency current which is coming from the input pair. That has not been changed. The only change which I have made is that the output load resistance. Okay. So ADC and your omega Z, all those portions will remain the same. Okay. In place of 1 plus S by omega P2, what now I have got is 1 plus S LD by RL and 1 plus S CL RL plus S square CL LD. Right? Now, if you work out, you will find that using this as a, using this transfer function, actually I can get a 1.7, roughly 72 times the bandwidth extension over your, like, over you can say prior dominant pole, which was 1 by RLCL. This is what you can prove. And the thing, so the important parameter is, you can, using this inductor, you can always get a more peaking. But more peaking is not good, because if you are causing a more phase distortion in the channel, in the equalizer response, that is going to hurt. So there are different bandwidth extension. With the bandwidth extension, you can get a more peaking and more bandwidth. You can also get a like a flat group delay. You can also get a maximally flat transfer function. So here, this 1.72 extension is for a maximally flat transfer function. There is some difference between how much it will be if you are going for a constant group delay bandwidth. So whichever way you do, in the end, whatever equalizer transfer function you have got, you should check it with the channel response and see what is the worst case vertical and horizontal eye openings. Okay, don't take it. So let me just give you an example. So let's say I have this channel response and this is Fs by 2. I use an equalizer such that I get a flat response till here, let's say ideally. Okay, and then I have another equalizer where I actually got this, which is not flat, but you are actually getting a wider bandwidth. So what do you think, which will perform better? How can you comment on that just by looking at the transfer function? So this more peaking which you are seeing right now, right? This more peaking can lead to your over equalization in the channel response, which can reduce your vertical and horizontal eye opening. So more peaking is not always good, and you can check that very well by simulating a worst case vertical and horizontal eye opening. For the, once you get the CTLE transfer function, you can get an impulse response in your like behavioral simulations, and then you can use that to get what CTLE response you want. Okay. So as a, like on CTLE, the concluding remarks we have that your output pole means if you are not using an inductor because of the area thing, you are limited in your peaking frequency because of the common mode output voltage, current and RL, right? So what can we do more to extend the peaking frequency or without using the inductor? Do you think there is anything else we can do to increase the peaking frequency, increase the gain, where my peaking value and my DC gain, you can say the load resistance, they are not coupled. Here you see, if you want to increase the DC gain, you increase RL. You increase RL, your peaking frequency comes in. That's what it is. Like VCM out and your peaking frequency is coupled. Or you basically increase the GM, so you are having a more power consumption. So in this particular CTLE, right, you see that your output common mode voltage, once you have given the output common mode voltage, right, you are actually dependent on your RL for that RL and I for the current, right? If I increase the RL, right, if I want to increase the gain, I have to increase GM, right? It's a GMRL, or you can say I increase RL if you are considering 1 plus GMRL by 2. If I increase RL for the DC gain, my peaking frequency comes in 1 by RLCL. That's the dominant pole at one point. So these two things are coupled. So if you look, and this is only happening actually at the output load thing. So you see that the input pair is not limiting the I am saying the input pair right now is the way I have drawn the ICTLE, which is coming from input pair. We have seen that the response of ICTLE is versus Vin is like this. Effectively means you can say I can change the zero location. It is still not limiting your peaking frequency. And if you start using only simple RL, means with the inductor you can get an extension, but that is one other thing. Inductors are depending on the area also. Whether you will use the inductor or not, that's a question. Or if you want to extend more, what will you do? Pardon? Current source load. Can you just go again? So I have, so let me just rephrase my question here so things become clear. We don't know what load I would want to have. So let's say this is some block which I don't know. And the only part which I know is at the output capacitor CL. And this is what I am looking at, V out. Right. I need a large gain from V out to ICTLE. Ideal requirement is this. Ideally, V out by ICTLE, I want large DC gain so that the signal is amplified at the output. Pardon? Inti? If you integrate the current, then again it's a limit, right? One thing is, will this be an open loop integrator? So the first thing is when you are integrating the current, the capacitance value and what current are you integrating, right? That will matter. So how much that the integration gain is, very much depends on the integration gain. And then for maintaining a DC output common mode voltage, you need to have a different feedback in the system. This is an open loop integrator. You are talking that I am injecting a current into a capacitor. But injecting a current into a capacitor does not necessarily say that you will have a larger gain over pushing the current into a load resistance. That will come somewhere, but here it doesn't say that clearly. So this is what, so let's look at the other thing which we want from this ideal CTLE. That one is V out by CTLE should have a large DC gain. Another thing is the output pole. Output pole should be at a very, it's like output pole is at a higher frequency. If the output pole is at high frequency, then the looking in impedance should be very low. That means RL should be very low. Pardon? Source follower at the output? Then what should be the input of the source follower? So if, let's say, let me just, okay. So what you are saying is, I am having ICTLE, and this goes where? Okay. So if you use a source follower, let's say you use another transistor and with some bias current, and this is the node you are going to use. You can surely do it, but then okay, you will be having a capacitance at this node coming in, C1 to begin. Yeah, surely at this particular place you are pushing the pole out. Okay, but this source follower should also have certain common mode voltage range. And this source, think about it, this source follower is going to add noise here without giving you any gain. No, if you look the two ideal requirements which I have pushed, that the current is pushed into an impedance which is very high, but the output impedance is very low. I think this block you have seen, right? If V out by I input is very high, that means what is high? Huh? Common gate amplifier will not do that. That's what I'm saying. Okay, let's just convert into the literal translation. If V out by I in is very high, V out by I in is, what is this called? Impedance or transimpedance? Transimpedance, right? You know that part or not? So if V out by I in is very high, that means I need a block with large transimpedance. Okay. And I need a low output impedance of this block. What? So, okay, let's first realize a transimpedance. So you have a gain block A. This is negative, this is positive, and this is, and let's say here your I in goes. RF, right? You have this Vx, so I in is equals to Vx minus V out by RF, and if A is a gain block, Vx is V out by A, right? Minus V out by A, which is minus V out into 1 plus 1 by A by RF. So you are having V out by I in is equals to RF, negative sign is fine, we can always use differential to get the right sign. This. As large RF I want is, again, in an ideal sense, as large RF I want, I can get a large gain. depending on, so let's say if A tends to infinity with a very large gain, this is minus RF. Now what is the output impedance of this block? Ideally 0. Huh? I do not care about the input impedance of this thing because I have the current which is a high pass current. I want from current to the output I want a gain. Means input impedance will also be low, as you said, this will be RF divided by the gain. Right? So means what is the, okay, let me just because there is some, so what is the input impedance? So I wrote this also as input impedance. So let's say Z1. So Z1 is equals to your Vx by I in. I can just write it in terms of that. Right. So this is Vx is V out by A. V out is you can say minus I in RF by 1 plus A times I in, which is RF by 1 plus A, right? Let's forget the sign right now. So this will tends to 0 if A tends to infinity. But this is not what I am. This will help you in with respect to whatever capacitance is coming at this node in a real implementation. Okay. And what's the output impedance of this? So let me just say this is Z out. Ideally, what is Z out? 0. So this is a block which can give you a large gain and push the output pole farther away. Okay. So let's say we use a more real system where we have, real system means you are realizing with the transconductance. You have a load like RO, you have CL, so positive, and then you have this RF and ICTLE here. Okay. Pardon? Yeah. So that will basically come as a secondary. So right now we have just realized that at the input you are having a very low impedance Z1. Okay. So that pole will, if you keep increasing the input pair size, then that pole will start becoming more dominant. Right? But the thing is, CL is actually the much larger load in the system. To begin with, that's the assumption I started with. Okay. So if I want, so this is ICTLE is Vx minus V out by RF, which is equals to, if this is positive and negative sign, minus GMVx plus V out by RO plus V out into SCL. Okay. So there is little bit work which you can. So what will happen here is you have Vx equals to V out plus I, let me just write it as I naught RF. Let's just write IRF, don't write ICTLE RF every time. And the other equation will be Vx is equals to, sorry, This one is 1. So I have this in this GM Vx current goes here. 1 plus GMRF Vx is equals to Vout into 1 plus RF by R0 plus SCL. Okay, now I will use just these two equations here to get a Vout plus IRF is equals to Vout into 1 plus RF by R0 CLRF is GMR. So you have Vout into 1 plus RF. Is there anything wrong in the equation? Vx is equals to RF 1 plus GMRF. Okay, so you have 1 plus RF by RO plus CLRF minus 1 minus GMRF is equals to IRF times 1 plus GMRF. Okay, this thing goes, we have Vout CLRF, now RF into 1 minus GMRO. This is 1 minus GMRO or 1 plus GMRO? Can someone check this? There's some sign got. So ICTL function, this is Vx minus Vout by RF. If I have positive here, negative, right? Let me just write this thing. Yes. So you can work out this equation as such. Let me just write you will have IRF into 1 plus, so not like this, Vout by I expression. Okay. And what's the DC gain of this Vout by I? If you assume that all the gains are going infinity, GMRO is much larger, this will be RF, right? And what's the pole in that assumption? Pole. If the input impedance looking in this block is going to be the infinite 0, and the pole is at ROCL, right? That is again very much under assumption. So you will have some parameters coming because of the GM and RF. So this one is CL and RO. Okay. Now this was Vout by I in. Any? Pardon? What GM? No, GM is a transconductance block which I am using. It's a GM block is like a V2I. Vx2I, yeah. So you know a transconductance block, right, which basically takes in the voltage and gives you the output current. And any transistor works like that. Any input pair transistor is you have a voltage control current source. Okay. So this is under approximate. Pardon? If GM is infinite, then it is almost, so I am writing in very much approximation. Yeah. How 1 by GM will come in parallel? Yeah. Right. So that will come, 1 by GM will come there. So if you, so this is, again, you have here RO in parallel with 1 over GM, right? This is what the thing it will be, yeah. Okay. Now it depends which is greater and which is smaller. If you say that GM 1 by GM is much smaller than RO, then this will turn out to be RF by 1 plus SCL over GM. It get independent of. The whole idea of doing this is that your V out by V in. Now let me write the previous gain stage, which was GM1 by 1 plus GM1 RS by 2. Okay. Now you have RF here for the DC gain. The things which you have controlled by RS and CS, those things have not changed. Gamma omega Z, right? What you get, another pole 1 plus SCL by GM, the GM of the second stage. You got more freedom in controlling the DC gain and the output pole. So if I write the same figure of merit for this now, this is normally called as, the whole block is called as CTLE, the trans impedance amplifier. Okay, so I have the CTLE which gives me output as a current I. It's called as CTIA actually, conventionally they call it that. And then I have this TIA, trans impedance amplifier with RF. Okay, and you have V input here, and this whole thing is called as CTIA. Just a convention, like what people use it. So now if I write the same figure of merit before, which was A peak by ADC, okay, and then the other parameter was, it's not A peak by ADC, it's ADC into, okay, I have, let me just, yeah, I got confused there. So you have ADC into A peak by ADC times the far pole. Same thing. So what I have now, this one is minimum of your gamma omega Z, and now this, the second pole is this pole, omega P2 coming from here, and omega P2 by omega Z into far off pole. Let me just say this is omega P2, this is ADC is sorry, you have ADC missing here. So okay, now let me just do the same thing, approximation, which is 2 RF by RS into gamma, if gamma omega Z is the gamma omega Z is the dominant pole, and omega P2 is GM, so this omega P2, which is basically GM by CL, right? And gamma, we know that gamma is equals to GM into RS by 2 under approximation. So you have now GM by CL, which was previously, multiplied by GM capital. Now I am using GM1 in this case. Let's say GM1 into RF. So here you see that this whole optimization is, it can be, if this is greater than 1, then you are extending the technology. Means you are extending the bandwidth of the, in a given technology. But the picture is not clear because we inserted a second stage in the system. So the question is, if we inserted a second stage, the power will be, there is power. So if I spend the total power same in both the cases, then that should be the comparison. Okay. So then what I say, I define now the figure of merit as whatever you have seen, ADC into ADC by a peak, sorry, a peak by ADC times bandwidth by power. Okay. So this, all these things we have seen for the previous case was GM by CL, right? And I am considering power is equals to VDD into I. Now the relation which we know already is that GM is equals to 2I by delta in my system. Means the gate overdrive which I am maintaining for the speed and the gain region is the same. So this is equals to, if I write, this is 2I by delta, so 2 by VDD into CL into delta for this, for the previous CTLE. Okay. Now for the second one, I have the same A peak by ADC and everything, which is actually GM1 by CL into GM RF by power, and I again want to spend the same amount of current in the system. So what do I have? I have GM1 GM RF by CL, VDD and I. Now small GM1 is consuming a current I1 and capital GM is consuming current I2, and the total current is I is equals to I1 plus I2. And I want to maximize this figure of merit, right? If I maximize this figure of merit, means I am having a better peak and gain, better bandwidth and lower power. So if you insert this I1 and I2 in terms of, use the same delta for both of, for simplicity reason here, and for, if you implement, you will find the same exit, same holds true also. So this will be RF, let's say 2 RF into I1 plus I2 by CL VDD I times delta. Are the units right here? So 2 RF I1. Okay. Now for maximizing this figure of merit, actually I1 and I2 is splitting equally. Pardon? What? Oh, sorry. I1 into I2. Yeah. Divide by delta square. You are right. What happened? Okay, yeah. So many mistakes. Okay, correct. Okay. Now this, if you find that how do you split the current I1 and I2, if the total current is the same, you will find I1 is equals to I2 equals to I by 2 for maximizing this figure. Okay. So if I just substitute that back here, I have RF I by CL VDD, so it's I by 2 I square, I goes CL VDD delta square. Okay. So the figure of merit, let's call this figure of merit 1, figure of merit 2. So this is equals to, I will just write 2 by CL VDD delta into I RF by 2 delta. Okay. So if you can, and this is all going for the signal current, this is not the, sorry, here I is the bias current, it's not the signal current. Because this is the I total current which I am consuming in the amplifier. So if IRF by 2 delta is greater than 1, IRF is in voltage, delta is in voltage, so the units are fine. If this is greater than 1, then your CTLE plus TIA means will have a better figure of merit as it is more power optimized and bandwidth optimized design as compared to CTLE. Otherwise, you can spend the same amount of power in CTLE itself and you can get a more simpler design. And both the designs which I am considering right now, they are without the considering the inductor in the system. So if you start increasing the more bandwidth, the approach is you start using inductor here or at some other places, because then the captions start coming at this node, so you need to resonate that too out. But that is more extension of this. Okay. So let's stop here. I think I exceeded my time.